Lesson 9.4 is on ellipses. An ellipse is formed when you have your second degree equation and a and b aren't equal to each other. So what that does to your circle equation is it kind of stretches out either vertically or horizontally. We're going to start with the equations on the right when the center of the ellipse is at 0, 0. As you look at these two shapes, you'll notice that it kind of looks like a circle that's either been stretched vertically or horizontally. That will be the key difference between the two shapes. In the equations, if you look down below, it's definitely looking different. The first thing you want to do when you're looking at the equation for an ellipse is decide, is it vertical or is it horizontal? And you'll know that in the definition down below, a squared, whatever that number is always greater than b squared. For example, in this first equation over here on the left, x squared over b squared plus y squared over a squared equals 1. Notice a is underneath the y variable, and that means it's a vertical ellipse. So the major axis is the y-axis. Now remember, the center is going to be right at 0, 0 in this format. So make sure that you are clear on that. Over on the right, we have the same kind of looking equation, but now a squared is underneath the x. So now your bigger number is under the x, and that means the x-axis is bigger, and the shape is a horizontal ellipse. You're going to have your center, and then you're going to have things called vertices. We had vertices for circles, but they were all in the same amount from the center. So we went to the right, to the left, up, down, whatever the length of the radius was. Well, now that's going to change for ellipses. We're not going to go the same amount in all directions. However, you will go the same amount on the major axis. You'll either go up and down the same amount, or you'll go over here, you'll go left or right. And that will give you those points either at the top and bottom, or the right side and left side. And then you're going to go for those minor vertices. So those minor vertices are the other 2 points that'll help you sketch your graph, and they're using the number that's underneath the other variable. For a vertical ellipse then, you'll actually go to the right and to the left, so on the right side and left side. And then for a horizontal ellipse, you'll count up and down. And you'll get those 4 boundary points very similar to what we did for circles, and you'll be able to sketch the shape of that ellipse. To graph the shape of an ellipse, the key features include these 4 elements. You want to figure out the type, which would be either vertical or horizontal. From there, you'll know what your major axis is. You'll want your center, and so far we know they're going to be 0, 0. That's how we'll start off. You'll want to figure out where your major vertices are and plot those 2 points, and then the minor vertices. And then the goal will be to sketch the shape of that ellipse. Let's try the 2 examples on the right. In looking at that first example, x squared over 25 plus y squared over 9 equals 1. The first step in stating your key features is determining the type. Will this shape be vertical or horizontal? Oops, and I don't know why I'm writing that. I meant to write the word type, sorry. Here we go. So look at the 2 denominators. We've got 25 and 9. So 25 is bigger, that would be our a squared. 9 is smaller, that's the b squared. The a squared is underneath the x, and that would make this type a horizontal ellipse. So almost like a football that's on its side. It's kind of like what it looks like when we're done. To find the center, we take a look at the x squared and y squared similar to what we did with circles. If there's nothing in parentheses with the x squared or y squared, right here, that means the center defaults to 0, 0. So that's pretty easy. Let's go ahead and plot that point. All right. To get our major vertices, so we'll say major vert for vertices. If a squared equals 25, then a equals the square root of 25, which would just be 5. So that's a perfect square. Kind of nice. From the center, if we count 5 to the right and put a dot, and 5 to the left and put a dot, those are our major vertices, just like that. For our minor vertices, we use the b squared term. The length for b is the square root of b squared. In this case, it's the square root of 9, which is 3. So again, from the center, we're just going to count up 3 and down 3. So I'm going to highlight these points to make them a little easier to see. I've got my up 3 and down 3, my right 5 and my left 5. So your goal is going to be to draw an oval through those 4 vertices. And when you're done, hopefully you have an oval type shape. All right, let's try the other example. Taking a look at x squared divided by 12 plus y squared over 36 equals 1. The first thing we want to do is determine the type of ellipse that we have. So the 12 is the smaller number. That's going to indicate it's b squared. 36 is bigger. That's a squared. And since that's underneath the y, this is going to be a vertical ellipse, which means it'll be taller than it is wider. Okay, then we want to find our center. And then again, that will be 0, 0. Since there's nothing being added to the parentheses, let's plot that. The third step is our major vertices. So if a squared is 36, a equals the square root of 36, which is 6. So from the center, we need to go up 6 since it's vertical, and down 6, like so. For our minor vertices, this one's a little trickier. Since the square root of 12 isn't a perfect square, we can find the exact value by breaking down 12 into 4 times 3, and the square root of 4 is 2. So we know that there are exactly 2 square root 3 in either direction. So then to approximate that, the square root of 12 is approximately 3.5. So on our graph, we'll have to go about 3.5 to the right. We'll just try to make that fit in there somewhere, and then 3.5 to the left. So again, I'm going to make those vertices just kind of a little bit more vibrant so they're easy to see on my paper. There we go. It's about 3.5, about 3.5. And our goal will be to connect these 4 vertices to show the shape for this vertical ellipse. That got a little aggressive. My iPad moved as I was drawing it, but you get the idea. There's your shape for that vertical ellipse. And both of these were centered at 0, 0. Things get a little bit more rigorous when we translate our center to HK. Similar to a circle, you'll know you have a translation if you have a parenthesis with x squared and y squared. As you can see, both of these equations do. Otherwise, it's pretty much just like what we did up above. You'll know if it's vertical or horizontal, again by looking at the bigger number. Remember, a squared is always going to be greater than b squared for these shapes. So you know you're going to have a major axis. If it's bigger underneath the y, it'll be on the y-axis. And if the bigger number is underneath the x, it will be the x-axis. That will tell you if it's vertical or horizontal. For the center, remember it's going to be HK, and it's opposite signs for both of them. And that's what we did for circles. Now the major and minor vertices are a little trickier to write out, but when we graph them, we're just going to move them in all the directions like we did up above. For those major vertices, on the vertical ellipse, the h will stay the same, but you're going to add a and then subtract a from the k part of the center, and that will move it up and down. The minor vertices, you'll actually add and subtract b to h. So you'll move it to the right and to the left. So I know that looks kind of tricky, but it's actually pretty easy once we do the actual sketch. And when the ellipse is horizontal, kind of that same idea. The bigger number's underneath the x, so now for our major vertices, we're going to take the h and we'll add and subtract the a to move those major vertices left and right. And then for the minor vertices, we'll add and subtract b to the k this time, and that will move them up and down. Oh, I didn't have any commas on the other ones. I don't want to be different for this shape, so that h stays the same, and then we'll subtract. But again, once you actually see those numbers and we move them around, it should be pretty similar to what we did when the center was at 0, 0. Let's try a couple of translated ellipses. The same key features apply here as they did when they were centered at 0, 0. For each of these equations, we'll state the key features and then sketch the graph. The first thing we want to do is determine the type. The bigger number is underneath the y-axis, which makes this ellipse vertical. The second thing we do is want to find that translated center. Remember, that's that HK. So if it's x plus 2 in parentheses, our center is going to go to -2. For the y minus 1, it will move up 1. So there's our new center. Let's go ahead and plot that. I'm going to zoom my screen out to make this really easy to see. Okay, -2, 1 is going to put us right there. Plot that in the center, or for the center. So now to get those major vertices. If a squared equals 16, then a is going to be the square root of 16, which is 4. And we're going to add that and subtract that to the y-coordinate of the center. So what we're going to do is keep the -2 the same, and from 1, we'll add 4, and then we'll subtract 4. So what that is going to do is move us up 4 to 5 at the top for that major vertice, and then from the center down 4 to -3. So those points would be -2, 5, and -2, -3. Just so that we know we're not going from 0, 0. So those are our two major vertices. To get the minor vertices, kind of that same process. Since the b value is, or b squared is 9, b is the square root of 9, which is 3. This means we're going to go right and left 3. We're going to take the x coordinate of the center, which is -2. We'll add 3, and then we'll take the x coordinate of the center and subtract 3. And that moves it right and left. That's all it does. So if we go 3 to the right, we'll be at 1, 1. And if we go 3 to the left, we'll be at -5, 1. And those are our minor vertices. Again, our goal is to connect these 4 coordinates with a smooth curve to form the shape of an ellipse. And our ellipse should look something like this when we're done. All right, let's try just one more. Again, we're going to determine the type and then list out the rest of our key features. Now this one's another one where we don't have a perfect square for one of our two denominators. Notice we have 24 and 9. So the bigger number is underneath the x. That's going to make this shape horizontal. There we go. The center is going to be at -3 and -2 for both. So we'll go -3, -2. Just put a big dot at that location on your graph. To get those major vertices, this one's going to take a little bit of extra work. So let's do those major vertices. We know that a squared is 24, so a is the square root of 24, which would break down into 4 times 6, which is 2 square root 6. So this is going to look really weird. Watch what happens here, and I'm sorry. If we do -3 plus 2 square root 6, and then -2, and then -3 minus 2 square root 6, -2, we're kind of stuck. Those don't actually simplify. So the square root of 2 is approximately 4.9. We'll go almost 5 in both directions. I'm going to count almost 5 to the right, so 1, 2, 3, 4, 5. I'm just going to kind of put it right at that point right there. And then almost 5 to the left, and I'll put it right about there. Pretty close to those endpoints right there. The minor vertices will go a little bit smoother, thankfully. To get those minor vertices, b is the square root of 9, which is just going to be 3. So we're going to go up and down from the center. That means we'll start from -3, we'll go -2, up 3, and then we'll go -2, down 3. So if we go up 3, that puts us up at 1. So that's at negative 3, 1. And if we count down 3, that puts us at negative 5. Let's make those endpoints, those vertices nice and clear for us. And we'll sketch the shape for our final ellipse. And it should look something like this when you're done. Finally, we have the task of completing the square. What we're going to be given is our equation in that second degree form, and we need to determine how we know it's going to be an ellipse and not a circle, and then write it in the standard form and list the key features. I think that's all we'll do. I don't think we're going to graph this one. Let's just do those parts, and that should be plenty. Remember the steps. In step 1, we want to move E over. We're going to subtract the 15. And then group our x terms and our y terms together. So we have 2x squared minus 12x. So they're even written in the right order for us. Plus y squared minus 2y. And we'll set that equal to negative 15. Now, when you have an ellipse, what's going to be unique about this is that the a and the b values aren't the same. And that means we're going to have to factor either the a out of the x terms or the b out of the y terms. Take a look at how we know. In that first equation, we have 2x squared minus 12x. The number in front of x squared has to be on the outside of the parenthesis. So watch what happens when I factor the 2 out. The x squared will just be by itself, and that's what we want. But then it's minus, and if I take 2 out of 12, that changes to 6x. So we've done factoring before, but now we have to see how this applies to our complete the square. Thankfully, the y squared is already by itself. There's nothing out in front, so we don't have to do anything there. Lucky. All right. So then here's step 2. In step 2, we take half of the c and d terms. So now we're going to take half of 6 and half of 2. Negative 6 is negative 3. And negative 3 squared is 9. So we've done this before. This is the pretty easy step. Half of negative 2 is negative 1. But when we square negative 1, we get positive 1. All right, step 3 is also a little tricky. We add it to the parentheses. So again, we still have that 2 out in front. X squared minus, let's make sure we can see that better. X squared minus 6x plus 9. Here's where we have to be careful. So I'm going to put a big star by this step. We added 9 into the parenthesis, but technically that 2 out in front means we added 18. So over on the right-hand side over here, I'm going to add 18 to the negative 15. I know, weird. We'll carry on. Because in that second parenthesis, y squared minus 2y plus 1, there isn't anything in front of the in front of the y squared to worry about, so we can just add 1 to the right there, like we did with circles. And we should be in good shape with that. Now when we combine all of our like terms here, we have negative 15 plus 18 plus 1, which is 4. Factor the parentheses, so we still have that 2 out in front. X squared minus 6x plus 9 is x minus 3 and x minus 3. Remember how that's kind of the same as what we found up here? And that's still consistent like it was with circles. Y squared minus 2y plus 1 will be y minus 1 and y minus 1. Just like it was up here. And then equals 4 on the right. So we have 2 times x minus 3 squared plus y minus 1 squared equals 4. Now, we're not totally done yet because the form for an ellipse is completely different than the form for a circle. We had fractions. The consistent thing was that 1 was on the right-hand side for all of our equations. We want 1 on that right-hand side as well. To get that, we have to divide. So whatever number's on the right, I'm going to divide to make it equal 1. But if I do that on the right, we have to do that on the left as well. And then what happens is this 2 cancels with the 4 to equal 2. And we end up with, x minus 3 squared over 2 plus y minus 1 squared all over 4. That doesn't go away. And then on the right side, we get 1. And that's the equation for our ellipse in its standard form. From there, we could list our key features, but I think I'm going to stop this video and I'll let you practice some of these on your own.